This is great to be here, to see a lot of people I haven't seen in a long time, and hear stories and tell stories about Stewart. I haven't seen Paul since, we were in touch over the years, but I haven't seen him since he was a little kid. And one of the things you didn't mention about your dad is he's kind of squeamish about things. So when Paul's baby teeth started coming in, Stewart didn't know what to do. But I remember what my dad did to me, and I did it to Paul, pulling his teeth out with a little roost, and it's his teeth look really good too, so I think it worked out okay. Yeah, great. So I want to tell you some stories about Stewart. Of course, probably the best person I know to tell stories about. And then I'll tell you a little bit about light Higgs bosons. I'm from New York. I grew up there. I went to school upstate New York for college, and for some reason I got it in my head I wanted to move to California for graduate school. I didn't know what I wanted to do. Well, I knew for some reason I wanted to go to Stanford. I don't know why. But I ended up going there, meeting people like Bob and Rick and a lot of other people here. But I really didn't know what I was going to do, and this person in the photograph changed my life because I was supposed to say hello to somebody at Stanford that one of my old professors knew, a guy named Stan Hanna that some of you hear about. and I went looking for Stan. I arrived in August of '77, and he wasn't around. And I'm looking for him. I stick my head in the office, and the person sitting behind the desk, her name is Kathy Eckstein now, but it was Kathy Peters, I think, at the time. I said, well, I'm looking for Stan Hanna. Is he available? And she says, no, he's away on travel, but you can talk to Stewart Friedman if you like. And I said, well, okay. Stewart was in his office. We chatted for, God, I think it was like an hour. He told me about experiments and things he was doing, and I remember being infected by that and wanting to pursue this sort of stuff with him, and that began 10 years of collaboration with Stewart. We started working together through graduate school, and then for 6 years at Argonne. I'll always remember those days and the lessons that I learned. One of the things I did over that time was that I measured nothing a lot of times. I actually had to go back and look at things we published, things were unpublished reports, and try and remember all of it. They're not all included here, but these are some interesting ones. The very first thing I did, we had a little accelerator at Stanford, a little single-ended Van de Graaff machine that I was able actually to change the knobs and ran things. And he said, look, some people I know are trying to figure out if there's a state we didn't know about in this beryllium-8 nucleus. And we did some little experiment and found nothing. I don't know what that was about, but it was probably from you. Probably something to do with Mass 8 with Bob and Tom. I don't know, you guys might remember, but there was something, it just occurred to me when I'm going through this that we were trying to do that. Around that time, Roberto Pache started talking about things called Higglets, which I guess we call axions now. So we started looking for these in nuclear decay, found nothing. But then I started working on my thesis experiment with my advisor, Alan Littke, who I know is here too. And we looked for free quarks, and that was a big endeavor, and found nothing, not only in E plus E minus annihilation, but we also looked in cosmic rays for quarks, tachyons, anomalously massive particles, and found nothing every time. It was exciting. So after I finished that, we went off to Argonne. I worked with Stewart and Jerry and a number of other people for a number of years, and that's where the light Higgs boson stuff comes from. I'll tell you about that in a second. With one of Stewart and Jerry's students, a guy named Mike Kropa, who has lots of stories to tell as well. We looked for magnetic monopoles in cosmic rays, found nothing. And then we worked on, the last thing I did at Argonne was that we worked on neutrino oscillations at LAMF. You're going to talk about that stuff later. Jerry will cover that, but that was another big nothing. That was a big nothing in many, many ways. I'm sure Jerry will get on to that. So I hadn't realized it, but I bet you I measured nothing more times with Stewart than you guys. But I learned so much from Stewart, and I remember him saying to me once, look, these things that you're picking up, these will be important when you have your own students someday. And of course, at the time I thought, yeah, right, mañana. But I did end up having a number of students, undergraduates, graduate students, and I started thinking about the things I learned from Stewart that I passed on to my students that were important to me. And so here are some anecdotes, and I think I got them right, but I might be making some of this stuff up, but who cares? So Stewart told me to write like Hemingway. In fact, I have my thesis here. Stewart had a copy of my thesis, so I'll bring that back with me. But I have this habit, as most of you know, when you start writing something down, you use too many words, and you have to start paring it down. He said Hemingway wrote very nice, concisely, never used too many words. So try and think that way. And for years after that, I would try and edit papers to get it clearly down to that point. I don't know if I got this right or not, but Gene Cummins, you're here, right? He told me that your father was Eugene O'Neill's editor. Oh, that's true. So he explained that's why you did this to him. And he did this to me. Alan was actually at CERN my last year of graduate school, writing my thesis. So Stewart worked with me a lot, paring all this stuff down. And I always remember that, and I've tried to teach students and other people to remember that. And when I told someone once, yeah, he said, learn that right like Hemingway. I said, yeah, sure, and do physics like Einstein, and everything will be great. Paul mentioned that Stewart liked to tease his friends. I'm glad to be counted in one of those, because we would fly airplanes a lot back and forth between Chicago and Los Alamos. And in those days, they give you, the choice. Do you want the chicken or do you want the fish? And Stewart would always mix them up in the advice to me. And it took me a while to figure that out, because I kept getting confused which way I was supposed to get. Should I get it or not? He loved to say, de gustibus non disputantem, which I think means, in questions of taste, there could be no dispute. He loved that. And it's one of the lessons I go back to, trying to figure out how to present various different things. Oh God, I love the guy. He told me this once, I thought, wow, that's brilliant. And I thought, wow, and I brought this to my students. I would tell them this. I would use this with them every time. I tell them, don't sit down and do a fancy calculation until you know about what you were supposed to get. Understand that. And I'm going through this. And then, I was already a professor. I think this was only like 10, 12 years ago, in fact. I'm reading through something, I think it was Space-Time Physics by Taylor and Wheeler, and it cites this as Wheeler's first moral principle or something like that. And, oh my gosh, I sent Stewart an email instantly. I said, Stewart, I just read that Wheeler is credited with this quote that you taught me that was so important to me. How dare Wheeler steal this from you? Stewart wrote back right away. He didn't answer too many emails, but he answered that one right away and said, yeah, it was something between us, but we've straightened it out. Stewart also told me that if you put together a talk, and if you have 2 slides for every minute you're supposed to talk, that's too many. So since I only got 20 minutes, I've already used up a bunch of slides. Let's go on and talk about light Higgs. This is a very abbreviated list of the lessons that I got from Stewart, but it's the ones I decided to put up. So what a light Higgs boson. And there'll be anecdotes in here too, but I should cover some physics. The idea was that if you're looking for a fundamental scalar, there are different ways to look at it. And one of the things he did teach me was to think of nuclei as elementary particles. I think this came from the elementary particle model of nuclei, Kim and Primakov, was it? You guys, that stuff. But it was a great way. It was exactly what Paul had mentioned about using precision techniques in atomic and nuclear physics to do particle physics. And if you can find 2 states, 2 zero-plus states, you can't emit a photon from that nuclear or whatever state, but it can emit a scalar. And if you're trying to look for scalars at massive, you obviously want 2 states that are separated by a lot. Turns out in helium-4, the ground state is separated from the first zero-plus excited state by about 20 MeV. So in principle, that's a good place to look for fundamental scalars. And we did this experiment. In fact, I think we owned the limit on light scalars, but as you'll see, there was something that Jerry likes to call shinky dancing in this, and I'll point that out in a second. You make the helium-4 by having a tritium target and bombarding it with protons of about 600 keV. So perfect for a little accelerator where you can get a lot of current. We had one of these at Argonne. So that was the experiment. It looked like this. There's the publication. Jordan Camp and Mike Kropo were a couple of grad students that were helpful in running and interpreting the experiment. They're great kids. I was in touch with both of them. I have some anecdotes about Stewart. Mike actually wrote me a long thing. I'll send it to you, Joyce. It was really nice. So here's a couple of things that are sort of interesting. We didn't use any kind of gas tritium target. You do it with something, the tritium implanted into erbium, and to keep the target from getting too hot so that the implanted tritium doesn't get out, the beam would be raster. Well, you didn't raster the beam, sorry. You'd move the target. There was this big wobbler system that we used because we really had to pour a lot of beam on target to get enough rate to have an interpretable result. And the problem with this was that tritium would escape. And tritium, as you know, is radioactive. So there was some issue about this because people thought, well, radiation, don't care. So the technique that the guy at Argonne, that Stewart liked to call Chicken George, the radiation safety officer, said that, well, when you finish the experiment, take the target off and look at it and see if it's damaged at all. So Stewart takes the thing off. He says, take a look. I said, no, I don't want that. So Stewart looks at it, and it looks okay. Maybe it's flaky a little bit. And he told Chicken George, and Chicken George said, okay, then you have to go pee in a cup because they have to see if he absorbed the tritium. Stewart was really pissed off about that. So here's how it works. Maybe you make a Higgs so that it comes out of that target more or less isotropically, travels some distance, and then decays in that big sodium iodide detector to E plus E minus pairs. Kind of looks like a photon. We ran the experiment with the beam on and off, randomly 50%. That's how we measured backgrounds, which turns out were kind of significant from cosmic rays and other things. One of the stories I'll tell you is about getting it published. Notice that we submitted it in September, didn't get published until January. And well, Stewart saved the day. I'll tell you about that too. So there's a nice tale that goes along with this. There was an anomaly in ionic X-rays in the 70s. Those are the papers. These are just from the references from our paper. So some guy, based on that anomaly, thought there might be a new scalar, did this experiment. Someone named Kohler, who I never met, but I think he was one of the referees. But then the X-ray anomaly went away. People did some other experiments. And then if someone realized that that old experiment would not see a Higgs boson because it was interpreted based on the X-ray anomaly, not what people knew about scalars by the time this came out. That person was Nimai Mukhopadhyay, who later became my colleague at RPI we knew each other for a number of years. He passed away in 2000. So anyway, there was this nice tale that went along with this. Turns out Kohler made some other big mistake that we could never figure out in this paper for helium-4. So we decided, what the hell, let's go do an experiment. I remember when Stewart came back, he was reading this paper on a trip when he came back from Europe working at ILL. And we were living in, usual, I was at your house when he got home. Maybe I picked him up at the airport or something. And he goes, look, I read this paper. This is great. This is the experiment we can do. We got all excited. We started thinking about how to do it right. And we started realizing, well, they made some other mistake in there, so we had to do a much better experiment. And that became the whole deal. This was our results. If you take that lead plug out, you see basically a captured gamma ray. It's not to the 0+ state. It's from the tail of the dipole resonance, but that's not important. We ran with uranium shielding and lead shielding. Uranium is better, except it came packed in these stainless steel cans, which made it very, it wasn't as dense effectively. So we replaced that with lead and ran some more. You can see some of the gamma rays leaking through, but there's no peak, and that means we saw no Higgs, no light Higgs boson. Experimentally, we excluded this. This is the region that the Kohler experiment excluded, and there's a few orders of magnitude that we got out of this. And then there's two different theories that you use to interpret it. This theory is from the X-ray anomaly. This is what Kohler used. So the fact that these don't overlap tells you that there was some mistake, but we didn't care. But it also means that this curve is almost useless. The curve that you care about is that one. That's the one that used the Higgs boson model that people had by the time, where you could actually calculate the width. That was exciting. So according to this, at least, we exclude this region of mass, which is like, down to low masses up to about 12 MeV. And I think that's what the particle data group picked up on. That's what we used. But there was a problem because that sensitivity was so small. To interpret that, you need to know the decay width of that 0+ state to a Higgs. And there's some stuff in here that's not so important. The most important thing is the coupling of the Higgs to the nucleons. And that modern theory had this way of writing down that coupling. And it had to do with the number of heavy quarks that were there for the Higgs to couple to. Okay, that's fine. Stewart had this brilliant idea. We're going to decide that the strange quark is heavy. And we're also going to decide that the top quark will be discovered. So we're going to put in 4 instead of 2. And that got you factor 2 in sensitivity, which was actually quite useful. Interestingly, that wasn't quite picked up by the referees, but they gave us some hassles, as I'll mention in a second. Stewart wrote this paper, and he wrote like Hemingway. I mean, it was beautiful. And I remember him being very pleased when he decided to use this word ubiquitous in the first paragraph to say this is the reason we have to go to it. And we talked about that. And then after we did this, and Brad Philippone helped me look up the referee reports for this, there's this one really long paper that said, well, I don't think this ought to be published, but if they want to publish it, here are all these things that they should do. So we said, okay, we'll do that. So one of the things Stewart taught me, by the way, was how to deal with referee reports. That's been useful. So Stewart, we did this, he wrote a letter to the editor of Barry Holstein, at least on the letterhead, but I just contacted Barry the other day. He doesn't remember any of this. I showed him the reports, said it probably got sent to somebody else. But he was great at mollifying the critics and saying this would be done. And the editor, I guess, wasn't Barry, writes Lackman, and said, we have to publish this because scalars are ubiquitous. So that's a reason to do it. And the paper got published, and we all had a good time. So Tony showed this photograph a couple times. It's probably the first photograph that I saw that really gave me some insight to what Stewart looked like when he was dressed as a graduate student. I remember the pants and the hair. I thought, that's Stewart. About how we used all this tape. But it also reminds me of how we go from being students to professors, having students, and how much that's meant to me over my career. So this thank you is not only to you, but also to Stewart. Thanks a lot.